YouTube video of me showing YouTube videos to my class. So I started to upload it, and then I was like, "Oh, I showed some YouTube videos," and then I took it down, and I'll have to go in and like cut that part out. Let's see. So what we're starting on today is a little bit of chemistry history. I'm gonna talk about. No, that's not what I want to do. Cancel any button. All right. I'm gonna talk about. Close your Chromebooks. I'm gonna talk about the. Huh?
Should I take notes?
No, take notes on paper.
On
Sorry.
paper.
Yeah. Unfortunately, there's people who are like, "Yeah, I'm taking notes," and then they're just video gaming it up. Yeah, it's not your fault. It's everybody's fault. And let's be honest, in your position, I would do the same thing. I'd just be like, "Yeah, I'm taking notes," and like YouTube video up or like reading a news story or something else. I doubt y'all are reading news stories, but you never know. Maybe you are. I'm not going to judge y'all. So today we're going to go over some history. This is actually the name of the assignment today, which is a long, stupid name. They should have come up with something different. But the assignment's name is Ancient Times, Dalton's Postulates, Thomson's Discovery of Electron Properties, Rutherford's Nuclear Atom, Bohr's Nuclear Atom. All of this together is like the name of the assignment, I think. So when you see it, you'll know that this is that assignment. But we're going to go through some history, how we knew about the atom a long, long time ago, and then we just listened to a dumb person, and for thousands of years we were like, no, we don't know about the atom. And then finally we rediscovered it. And stuff like this just makes me wonder, like, where we would be if we had listened to some of those really early people and like learned about the atom earlier on. Like, would we all have flying cars and like no diseases and like machines that just healed us instantly and we'd all be super rich? Or would we just kind of be the same as where we're at now? If you can't tell, I like science fiction stuff. It's pretty interesting. Like, I'm not recommending you watch this show because it's kind of an adult show, but I watched this one show called Altered Carbon, and basically, like, you can download your consciousness into like almost like a little flash drive that they like keep in your neck. And so the crazy part is if your body dies, but your little flash drive, which they call stack, is intact, they can just like stick you in a different body. Or if you're rich, you can have like a new body grown from like stem cells or just created or something. But one of the weird parts that they do in a certain part of the show, one of the main characters, like a police officer lady, is Hispanic, and they have Dios de los Muertos. And she gets her grandma's stack and like spins up her grandma in like the body of like a criminal. It's like a big bald white dude with like tattoos, and he looks real scary. And she brings her grandma back for Dios de los Muertos to like have like a celebration with the family. And it's an interesting part of the show because they kind of talk about how, and I'm getting way off topic here, I'm sorry, but we'll just spend a second talking about it. How they can like bring family members back for important events. Like if someone's getting married, you can rent a body and like spin up your grandma and your grandpa so they can be there to see your marriage, even though they're old and they've already passed away. They can still be a part of those like important events. And it's really interesting. Like, obviously it's science fiction and it's just like something that they wrote in there, but it's a crazy thing to think about. And it's not technically probably not impossible at some point in time, definitely now. But maybe one day in the future, we can survive on a flash drive somewhere. Yeah, I don't know that we would want to do that, but and even in the show, like, there's religious people who don't want that done. There's good things and bad things to it. It's a really crazy show, but probably a little adult. Don't go home and be like, Mr. Bailey told me to watch this. No, I have video evidence that I specifically told you not to watch it. So back on track right now. The development of the atomic theory. We're going to start very, very early, literally in ancient times. And we start in ancient times with Democritus. Democritus was very smart. He was not one of the dumb guys. Although we don't necessarily recognize his name, I don't know that he brought us democracy. Maybe he did. Maybe democracy is named after Democritus. But obviously, very smart guy. He proposed the existence of atomos. And atomos is basically the root word for atoms. They were indivisible, indestructible particles that made up matter. And this was basically from that thought concept that, if I had a knife small enough, could I just keep cutting something in half and keep cutting that in half and keep cutting that in half? Would I just be able to cut it in half forever to infinity? Or would I get to a stopping point where I got something so small, it didn't matter how small my knife was or what kind of technology I had, I just couldn't cut that thing in half? And they said yes, and that thing would be atomos. They would be indivisible. I could not break them in half any further down. It was just the base unit thing, and you couldn't go any smaller. They would be indestructible, and they basically make up matter, which, as we know, is everything. For not having like any details or any technology or anything, this is like remarkably correct. For being literally back in ancient times in ancient Greece. Who knows if we'd listened to this guy and kept this idea around, how far we would have gotten by now. Maybe we're at the same point. Maybe the technology doesn't develop any faster just because we know about things. But maybe it does. Who knows? He proposed that different types of atomos possess different properties, which is true. Different types of atoms of different elements do different things. A silver atom is different than a gold atom, is different from a platinum atom. They all have different properties. He proposed that changes in matter produced by changes in the composition of groups containing different atoms. This is basically saying that chemical reactions exist. If you mix up the atoms and they get into different groups, that's going to give me something different. Hello? Yes, they are. Yes, I already printed. Well, I saved one to the drive. Yeah. Okay. Sorry about that. All right. Okay. Bye. Okay. So yeah, he knew about atoms. He knew that they were indivisible. That different types had different properties, and he proposed like the idea of chemical reactions and chemical changes happening. Even that they move through empty space, which is a crazy concept. That you had atoms that had very, very large distances in between them, and they moved through like essentially nothing, empty space. This is crazy stuff to think about. When you get into math and numbers, it took us a very long time to understand the concept of zero, to have a number for zero and talk about nothing. And so that he's talking about empty space this early is pretty crazy. Then comes along Aristotle. And we know Aristotle's name. He's probably a little bit more famous than Democritus. Aristotle ruined everything. I don't know why. Maybe just because this is a little bit complicated and we like to keep things simple. But Aristotle screwed everything up. And he basically came along and was like, no, atoms are dumb. We shouldn't talk about those. We should talk about how matter is composed of earth, air, fire, and water. And all things are just these four essential elements. And that's it. Earth, air, fire, water, done. Super easy. We don't have to think very hard. It just is what it is. And this stayed around. There's no such thing as empty space. He got rid of empty space for us. It's all just earth, air, fire, and water. And basically the idea of the atom was dismissed for thousands of years. It literally took us thousands of years to get back just to this point where we accepted the fact that there were atoms that were tiny, indivisible things that had different properties and moved through empty space. Aristotle ruined it for us. Literally, we could have flying cars and be like the Jetsons with like robot butlers. It's a shame. He was watching too much Avatar. Maybe, yeah. He just got into the elements too much, and he's like, I want to be a firebender. I don't know what his deal was, and I'm sure he's really smart because we all know his name. Hopefully, he's not famous for this thing because this is really disappointing. But yeah, when I learned about this, I was like, oh, this is so disappointing. And so, sometimes people come out with crazy stuff. Even if it sounds stupid, and maybe it will be stupid, it doesn't hurt to be like, you know what? Could be true. Prove it. Let's hear the guy out. Let's hear Democritus out and see if these atomos really exist. So it took us thousands of years, and then finally we get back to Dalton, and you can see from Dalton's picture, this is not ancient times anymore. I think they're going to give us a date in a little bit. But Dalton created the idea of a new atomic theory. He based this on experiments that he did. He said that the elements are made of small indivisible particles called atoms, not any different than what Democritus said. The atoms of an element are identical to each other and different from other atoms of other elements. Again, Democritus had already said this thousands of years ago. And that chemical reactions occur when atoms are combined, separated, or rearranged in simplified whole number ratios. Kind of the same thing as Democritus said, but a little bit more detailed. He's talking about whole number ratios and giving a better definition for what a chemical reaction is. He did point out that atoms are not created or destroyed in chemical reactions. They just get moved around. If I take hydrogen and oxygen in water form, and I do a chemical reaction that breaks up that water into something else, that hydrogen and that oxygen will still be there. It's still an atom of hydrogen. It's still an atom of oxygen. We do have a couple revisions for today. The atom is the smallest unit of an element that demonstrates the properties of that element. Let me see. Let's just see when Dalton was alive. Oops, it went away. Dalton, atomic theory. John Dalton, that's his name. Is there a Wikipedia page? This is not important. I shouldn't be looking this up. 1844. 1766 to 1844. So he probably did this around the turn of the century, 1800s. So probably well after, like 2,000 years after Democritus was doing his stuff. The point of the atom is the smallest unit of an element that demonstrates the properties of that element all the way down to a molecular level. If it's a metal that conducts electricity and isn't very hard, that atom will have the same properties of that. It will reflect the same light. It will do the same things. If you get any smaller, you lose those properties. If you start to collect atoms together, they still retain those properties. Atoms of the same element can have different masses. This is the idea of isotopes. He did not know about isotopes at the time. It took us a little while to figure those out. We'll talk about isotopes later. And then atoms can be divided into subatomic particles. That's actually relatively recent. It took us a while to get to the point where we got an understanding of subatomic particles, and we're still trying to figure that out. So Dalton was the first one with his idea of the atom, and kind of building on what Democritus had. Then we get Thomson's discovery of the electron, and this is interesting because the electron was the first part of the atom that we discovered. We still didn't understand neutrons and protons. We didn't know about the nucleus. We just figured out electrons first. And it kind of makes sense when we talk about atoms, electrons are the ones that actually do things. The neutrons and the protons are relatively boring. When you have chemical reactions or you have something crazy happening in chemistry, usually that's the electrons doing that, not the protons and neutrons. So the fact that he discovered them first before anything else is not too crazy. What he did, he took a cathode ray. I used to have a giant old TV back there. The old, like, big, thick glass TVs. That is essentially a cathode tube. It's a lot more complicated than this, but they would use electricity, pass it through some plates, and it would shine on the inside of this glass tube, literally, and that's how you would get your picture. Obviously, a lot more complicated than this one, but that is a cathode tube TV. It uses the exact same terminology for the tube. So what he did, he made these cathode rays, which they still didn't even really understand. They were just using the technology and trying to figure out what it was. And he's like, okay, let me put some magnets on this thing and see what happens. And so he took a positive magnet and a negative magnet and put them on each side And what he noticed was that the cathode ray bent, where before it would go straight in the middle, it started to bend as it went by these plates. And we already at this point know that positives and negatives, like opposites attract and like charges repel each other. And so because it moved away from the negative plate and towards the positive plate, he theorized that this beam of cathode rays are electrons. They're negative particles. And they moved away from the negative plate because like ones repel, and it moved towards the positive plate because opposites attract. So he proposed the electron. This is J.J. Thomson. It's a negatively charged subatomic particle, smaller than the atom as itself. The mass of an electron is much smaller than the least massive atom. So we knew that they were really, really small compared to the overall weight of an atom. Almost massless, not really massless, but mass so small that they're very insignificant to the entire atom of itself. So he proved that subatomic particles exist. And he had to make a model. So they're like, okay, you got these electrons. How do they work? What does the atom look like? He overestimated, well, he's trying to just find something to relate it to people. He overestimated the popularity of plum pudding. Maybe that was like his favorite dessert, but I don't think anybody in this classroom has ever had plum pudding. And so when I say the plum pudding model, you're not all like, oh, yeah, like the plum pudding. I know now. I see it in my head, the plum pudding model. So he maybe liked the dessert a little bit too much. But the idea of the plum pudding model is your pudding is positively charged. So positively charged area is your pudding. Basically, like we just have this big ball of positive stuff. I don't know. Let's call it pudding. And then your electrons are going to be like the negatively charged plums that are in the pudding that make it so delicious. And so this was the plum pudding model. Basically like I don't know, like a pudding with plums inside of it. We don't really eat anything like this nowadays. What would this be like? I don't know. Maybe like boba tea. So who drinks the boba tea? Like the positively charged tea and the negatively charged boba bubbles inside. Yeah, pomegranate seeds. Yeah, or a chia seed thing. My wife will like violently throw up if she drinks pomegranate anything. So yeah, we don't drink pomegranate stuff in my house.
But like vanilla wafer stuff with the pudding.
Yeah. Banana pudding now. If you said the banana pudding model and the pudding's positive and the wafers are negative, we'd all be on board. We're like, yeah, I got you. Little family secret. My mom makes a great banana pudding. Gotta have lots of bananas in there, but the pudding isn't banana flavored pudding. You use vanilla pudding instead of banana pudding, and it's best. You put the bananas in there, but the bananas bring the banana flavor. The pudding doesn't have to be banana flavored. It can just be vanilla. It's good. But basically, the electrons are scattered throughout the mass. He failed to correctly describe the structure. We know now atoms don't exist like in plum pudding or banana pudding models. It's something different. So then we get to Rutherford. Rutherford does this really cool gold foil experiment. One of the weird things about gold is so soft. We can roll gold into like a foil sheet of gold that's literally just a couple atoms thick. It's extremely, extremely thin. And so he got some of this really thin gold foil. He got a radioactive source that would release radioactive elements. What are you doing over there?
No.
Crumbling stuff up? He would release these radioactive elements out of a box that had a radioactive source in it and basically shoot radioactive particles at the gold foil. And he's like, let's see what happens. And basically what it turns out is, like this gold foil, it looks solid. It looks like a piece of like foil that you would use in your kitchen. But it acted like a chain link fence. A bunch of stuff, almost all the stuff would just go right through it. Like you're shooting BBs at a chain link fence. Most of it's going to go right through without touching anything. A couple things would hit the chain link just a little bit and like reflect off to the side, not go straight through, but still get through the fence, but kind of come off the side. And then every once in a while, very rarely, something would hit the gold foil and actually be bounced back and not make it through. Looking at the gold foil, you're thinking, there's nothing getting through that. It's solid. Like I can't see any holes. There's no holes in there. But almost everything made it through without punching a hole. Only a couple things actually got stopped by the gold foil. So what that told Rutherford is, even if you have a bunch of atoms connected together in a solid, they're mostly empty space. There's a couple points in the very center that are solid, but almost everything is empty space in an atom. The vast majority of it, even when you have a solid. And so that led us to the idea of the nucleus. The nucleus is a small, dense, positively charged area in the center of an atom where your protons and your neutrons are found. The electrons are on the outside, and they're so small that the vast majority of your atom is just empty space. Even in something like a solid like this, when you get down to the molecular level, most of your solid is empty space in between those nuclei. And so the nuclei of atoms repelled some positively charged alpha particles, while other alpha particles traveled through empty space and just went right through it. And so the gold foil, think of the gold foil kind of like a chain link fence. It'll stop some things, especially big things. Like my hand's not going to be able to go through the foil. Well, I mean, it will, but I'll have to break it. But really small atoms like alpha particles that he used went right through like it was nothing. So he designed this idea of the nucleus. You have your small nucleus in the middle. You have your very tiny electrons orbiting the outside, kind of like planets. This is like a classic view of what an atom looks like. Like the planets rotate around the sun, but kind of all on different angles. This was a lot better. This is much, much better than the plum pudding model, but it did have a problem. Let's see where they get to the problems in a little bit. They talk about the proton, the neutron. The electron orbits were wrong. They just didn't understand the way that electrons orbit. And we're even to the point now, we don't fully understand it, but we accept that we don't understand it. And so we create a model that is a little bit different. And we'll talk about that later. Then you get to Bohr. Bohr's nuclear atom, he discovered that the emission spectrum of hydrogen contains only certain frequencies. So he only did this for hydrogen. Basically, he took some energy and he pushed electrons around. Let me show you real quick. I'm turning the lights on. He took some energy and he pushed electrons around, and he kind of designed this, this idea of an atom. So this is your nucleus. Let's say there's an electron right here. And let's put another one over here, another orbit. And basically by putting energy in, he would push this electron up to a different level. Or maybe even push it up to the second level. And then when he stopped putting energy in, the electron doesn't want to stay up there. That's not where it's naturally at. It would fall back down. But if you have to put energy in to get it up there, it's going to release energy when it goes back down. And so it will release light at a certain frequency. And by studying this light that comes out, which they're showing you over here, by studying this light and what color it is, the wavelength of the light tells you about the energy that you had to put in, which told him about the distance those electrons had to be pushed. And so he got the idea, and let me take my computer so everybody sees this. He got the idea that your electrons were at different levels away from the nucleus. We call them orbital levels. This still exists today. We understand this fully. His science on the light and the different levels were correct, but his understanding of where the electrons were at were wrong. We had to learn a lot more about that. But this really gets us to the point where we fully understand the atom, and we can really start to do a lot of experimentation on it. Let's see. So if I turn this back out, these are kind of yellow, but you can see you have the circular orbits, just like the planets around the sun, where your electron is orbiting the nucleus that has your protons and your neutrons inside of it. What he got wrong was he only did hydrogen. He didn't do any other elements. And he did not explain chemical properties and how your atoms and different electrons have different chemical properties. And we know now that electrons do not revolve around the nucleus in circular orbits. We got to the point where, I think I'm going to talk about this on a different night. No, it's in here, so we'll talk about it. there's some stupid physics jokes. They're not stupid. They're actually pretty funny, but unless you know what they're talking about, they're stupid. You can't know the speed and location of an electron, at least right now with our technology. So here's the idea. Sorry, should have warned you. The lights are coming back on. The smallest thing we can manipulate is an electron. It's the smallest thing we can put, for lack of a better term, put in a gun and shoot at things. So imagine being in the gym, and I turn the lights out and blindfold everybody. You can't see anything. And I give you all one basketball, and then I throw another basketball into just the center of the gym. And your job is to randomly throw basketballs onto the floor and listen to see if it sounds like it hit the floor or sounds like it hit another basketball. And that's your only way to locate the basketballs, because you can't see them. So you literally just shoot other basketballs at them and see what happens. That's the way we try to look for electrons. The only way we can see electrons is if we shoot other electrons at them and we hit them. The problem is, if I hit another electron with an electron, is it still in the same place? No, I've just moved it. And so it creates this paradox where we can know the location. Where are we at? We can know the location of an electron, but if we know the location, we've changed its speed, and we don't know what speed it's going. We can know the speed of an electron by doing a different type of experiment, but if I know the speed of it, I have no idea where it's at. And it just gets down to the math and the way that we look at things with electrons. We can know one of them, but not the other. We can't know both at the same time. So we can know the location, but not the speed. So essentially, having a model like this that says, hey, I have these orbits, I have these electrons, this is where my electron is at. Here it is, it's right here. This is wrong. What we know now is, let me erase these a little bit. We basically have these clouds, and they're different shapes and they have different orientations. But basically we say, in this cloud, this is an electron cloud, you've got let's say a 95% chance at any given point in time that the electron is in there. Maybe it's not in there. Maybe it is. And if it is in there, I have no idea exactly where it's at. It's just somewhere in there. That's how we think of electrons now. And so it's not even like we got it 100% figured out. It's more that we've got it more figured out than we used to, and we understand that we have limitations, that we can't just point to it and be like, that's the electron. I got it done. So that's what we figured out after Bohr. Bohr really led us to a great place, and a lot of his work is still very valid, just not the model that he created of electrons. So that's the end today. How much time do we have left? Not very long. Nah, we got a little bit of time, like maybe 15 minutes, right? Yeah. So I'm going to assign the sapling. Go ahead and open up the Chromebook, and we'll get that going. Let's see. They're going to ask you about all these people. And remember, when you get here, the assignment will be up. But if you scroll down, we're starting chapter 3 today. If you scroll down to chapter 3, you can click on this study sheet right here underneath the assignment. Ancient Times, Dalton's Postulate. You can click on this study sheet, and it will take you to a little PDF that tells you about all these people and what they did. So just keep that in mind. And give me just a second, and the assignment will be assigned, if you will. Save and continue. All right, it's up. Maybe refresh your page and you should be able to see it. If you have any questions about this, let me know. I'm going to stop this and post it on the YouTubes. Thanks for watching the video, I guess. I highly doubt that anybody watches these videos to the end. I have the YouTube channel gives me analytics. And it's like 3 people watched this video. Average viewing time was 15 seconds. And I know one of them is usually me because I make sure that it works right. So good times, good times.